So today we're going to keep talking about confidence levels and confidence intervals like we were talking about last time. And the confidence level is how, confident you are in the current method you're using. Like how confident are you in this math that you're doing? And there's different values that we tend to use. The most common are 90, 95, 99. I think in this class, these are the only three we will use. And the single most common is 95%. And it means exactly as you might think. The larger this number is, the more confident you are in your answer. And as an example of that, if I said, guess my age within 1 year, 5 years, or 10 years, so plus or minus 1, plus or minus 5, or plus or minus 10, if I said, which one would you be most confident in, like your ability to correctly guess my age, hopefully you would choose 10 years. Obviously, if you could guess with a 10-year window on each side, 10-year margin of error on each side, you probably would get my age, hopefully, or you'd be incredibly insulting. He's 70. Bad guess. So the idea is you'd have the most confidence in the largest interval, and you probably wouldn't be super confident in this guess, this 1 year guess, if you had to guess my age within 1 year. It's a bit difficult, maybe. And that's just how these levels work. So 99% is going to be the largest interval. 90 is going to be the smallest interval of the three. This is fairly important too. Our confidence is in the methodology, so what we're doing with the math, as opposed to the interval itself. We're not saying that this interval has a 90% chance of being correct. It either is correct or is not correct, but we're confident in our method. And I'll try and explain what I mean by that in the next slide. But the main idea, that's something maybe worth writing down, is the greater the confidence level, the wider the interval. That's fairly important and hopefully intuitive. The more confident you are, it's because you have a wider range of guesses. So it says if we generate an interval, okay, so this is kind of talking about the idea behind the methodology. If we were to generate an interval estimate over and over and over again, so we take a sample, get an interval, take a sample, get an interval, take a sample, get an interval, like over and over and over again, about 95% of those intervals would be correct. That's the idea behind this 95% confidence. If you were to construct many, many, many intervals, about 95% of those would correctly capture the true value. But the other side of that means that 5% of the time we recognize it'll not capture it. So there's a trade-off there. And this is a visualization of that. So there is a population proportion. Let's say the percent heads on a coin, maybe it's a 50%. That's the true proportion. You over the long run will get 50% heads. These blue and orange lines here represent confidence intervals based on samples. So you flip the coin, 20 times, and you figure out what proportion of heads you got. So if you got 35% heads, you got kind of unlucky this time. Your interval might look like this. This interval fails to capture that true proportion. But notice that the vast majority of intervals, through flipping your coin 20 times, will capture that true value of 50%. About 95% of the time if you're doing 95% confidence. So the main idea here is the orange ones failed to capture the true value, and we recognize that happens. When you do 95% confidence, it only will capture the true value 95% of the time. And we already talked about margin of error, which we abbreviate with an M. But the way we calculate that is we take our critical value and we multiply it by the standard deviation of p hat. So the margin of error is equal to the critical value times the standard deviation of p hat. And standard error is the same thing as standard deviation. The only difference are these little hats on these guys. So when the hats are missing, it's standard deviation. When the hats are there, it's standard error. And the reason we call it standard error is there's a little bit more error involved because you're using sample values to estimate the true proportion. And you probably already have that written down from yesterday, but it wouldn't hurt to have, the margin of error is equal to the critical value times the standard error. written down somewhere. And I'll show you what I had last time. Maybe this will ring a bell and you'll be like, oh yeah, I remember that. So the PowerPoint slide had margin of error is equal to 1.96, which was just a critical value, which again changes based on the confidence level. It was for 95%, times what's called the standard error. And the reason why we're using standard error is because we don't know what P is. This is how you find margin of error. Critical value times standard error. Okay, these are definitely worth writing down. There is a way to find these in like a calculator, but it would be harder for you to learn the method to find them. It would be using inverse norm than it is to just write these down. 90% confidence goes with a critical value of 1.645. 95% confidence, which is the one I already had written down, goes with 1.96. 99% confidence goes with 2.576. These values do not change when we're talking about proportions, confidence levels with proportions. So they are worth writing down. I can't stress that enough. You want to write these down. And make sure you don't just write 1.645. Make sure you tell yourself it goes with 90% confidence. These are Googleable. I don't know if that's a word or not, but if you forget them, I mean, you can always come back to the video or you can Google them. There is a way to find them using inverse norm. It's just, it does require you to recognize how inverse norm works, and it's just easier to write these three down. Leave them there for just another second or so. All right. Suppose we wanted to know the proportion of students wearing tennis shoes today. It would be obviously difficult to count all the students wearing tennis shoes and all the students in the school to compute the true proportion, so the population proportion, P. So it would be kind of difficult to do a census, is what this is saying. However, we could take a sample and then estimate that proportion using a 95% confidence interval. We could say, I think the true proportion is somewhere between these two. So here are just some like ideas behind the confidence level. As your sample size increases, as you go up in the sample size, the margin of error goes down. And hopefully that makes kind of intuitive sense. If you gather more data, you're going to have less error involved in your answer. Hopefully that's an intuitive idea. The more people involved in your sample, the more sure you are in your sample, the less error you're going to have inherent in it. As you increase your confidence level, the margin of error increases. And I'll remind you about this right here. You'd be most confident in the widest interval. The more confident you are, if you want to be more confident, you have to increase the size of your interval. So the larger your confidence level, if you're 99% confident, you're going to have a very wide interval. That's what this one's saying right here. A way to counteract that, though, because we don't like large intervals necessarily. We don't want large margin of error. A way to counteract that is to increase your sample size. So you can be very confident, but if you take a larger sample, it kind of counteracts that margin of error. And this is kind of important. As p-hat increases to 50%, the margin of error increases. So 50% is the largest margin of error. If your sample proportion is 50%, you will get the largest possible margin of error. And as you decrease from 50%, your margin of error decreases back down. So 50% has the highest margin of error. You don't really have control over that, what your sample ends up being. It's not like you can control that you get 50% for your sample, but this is just a fact, these three things here. The main ones I think are important are, as you increase sample size, margin of error goes down. As you increase your confidence level, margin of error goes up. Those are probably worth making note of. And then maybe this could be like a good true or false question, I don't know. The largest margin of error is produced with p-hat is equal to 0.5, exclamation mark. So you know it's important. I think that's how that works. Mr. Sample, I assume. I think that's a James Bond reference. I don't know, though. So it says, true or false? When selecting a sample, it does not matter if the sample is selected randomly. Hopefully you guys are on board with the idea that that's very false. Randomization is incredibly important. It reduces bias. If you don't have a random sample, your sample is going to be probably pretty biased. So you need to have a random sample. In order to compute confidence intervals, the sample size can be really big, really small, or any size in between. That's not true. Remember yesterday we were talking about, or I guess 2 days ago for this cohort, how n times p and n times 1 minus p have to be greater than or equal to 10 in order to have normality. Those are things we have to check in order for normality. And then number 3, in order to compute the confidence intervals, the sampling distribution of p hat can be skewed. No, we want a normal normal sampling distribution, which is what this n times p and n times 1 minus p checks. If these are both greater than or equal to 10, then the sampling distribution of p hat is normal, which is what all of our math is going to be based on. So it's important that we have a normal sampling distribution. So the conditions for computing a confidence interval, the things we are going to check before we do a confidence interval, is that we have independently selected items, whatever we're talking about. And the way we check for that independence is if it says it's randomly selected, or if there's an idea of randomness in how they're chosen. We don't want a biased sample. That's like the main idea. We don't want our sample to be biased. So that's the first condition we're going to check. We then want to check that our sampling distribution is approximately normal. The way we check that is that n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. So here's an example. In a recent study, 45% of a randomly selected sample of 496 American adults said they do not get enough sleep each night. Can relate. Have the conditions been met for us to do a confidence interval? Let's see. Well, first of all, we do have a random sample. It says it right here. It's a random sample. So we've checked off the independence condition. Second of all, we're going to check to see if we have a normal distribution. And so we do n times, in this case, p hat. We don't know what p is, so we're going to use our sample value of 45%. Whenever we don't know p, we use p hat as a substitute. It's not ideal. It's just all we have in its place. So n times p is 223.2, which is definitely greater than 10 or equal to 10. And 496 times 55, that's just 1 minus 0.45. So I'm just doing n times p and n times 1 minus p. That's also greater than or equal to 10. And so since that's true, the sampling distribution of p hat is approximately normal. Once you have checked those assumptions or conditions like we just did, make sure you always check those first. These are the things we have to check. We have a random sample and that we have n times p hat, n times 1 minus p hat greater than or equal to 10. Once you've checked these, we can move on to actually calculating our confidence interval. The formula we learned yesterday will work, which would be p hat plus the margin of error, plus or minus the margin of error. And I'll also show you a way to do it in the calculator in about, I don't know, maybe 5 minutes. And then finally, we have a conclusion. So these are the 3 parts to doing a confidence interval. We check our conditions, make sure our math is appropriate. We do the actual math. And in step 3, and this is a really big part about statistics, is we interpret our answer. So statistics is kind of boring if you just get numbers, because a calculator does that for you. The whole point of statistics really is to interpret those numbers. And so here is something you need to write down. This is the conclusion for a confidence interval. We are blank % confident, so we're like 95% confident, 99% confident, 99, 95, 90, that the population proportion of whatever we're talking about is between blah and blah, the two endpoints of our confidence interval. So for example, we are 95% confident that the population proportion of happy puppies is between 80% and 90%. Most puppies are probably pretty happy. They don't have the weight of the world on them, most likely. So this is something you want to write down, memorize. I'll leave it there for a little bit longer just so you can get that. Make sure you replace the word context with the actual context of the problem. Don't just write context. It's always funny when that happens on like a test or something, but it means the context of the current situation as opposed to the word context. All right, let's try the full thing, guys. What do you say? Nothing. Okay, well, then I will take that as you saying you do want to do this problem. So in a random sample of 80 members at a large health gym, 38 drive an American-made car. We want to get a 95% confidence interval for the proportion of health gym members. That's a weird health gym members that drive American-made cars. So we don't have time to do a census of all the 1,000 people or however many people come to this gym, but we did take a sample, a random sample of 80 members, and we're going to use that sample to get an estimate for what the true value is, and we're going to use a 95% confidence interval to do that. First thing we need to do is find the point estimate. That's just the sample proportion in this case, and that's 38 out of the 80. So remember, p hat is just x over n. So exactly 47.5% of our sample drives an American-made car. That's the point estimate. Next up, we have to check our conditions. We need to have a random sample, and we do. It's a random sample of members at a large health gym. Okay. I don't know about that. Like, I've never heard health gym before. Step 2, we want to check for normality. Is n times p, and really it's n times p hat. These should have hats on them. And n times 1 minus p hat, are they greater than or equal to 10? And yeah, 38 and 42 are, in fact, larger than or equal to 10. So the sampling distribution is approximately normal. We've checked our two conditions. These need to be met in order to do the next step, which is our math. And I will show you how to do this in the calculator. So this is a good time for that. If you don't happen to have a TI calculator, all hope is not lost. There are plenty of online calculators. If you just Google confidence interval for proportions calculator, something like that. I don't know exactly the combination of words that would get you there the quickest, but I guarantee you there are tons of calculators online that can do confidence intervals. If you have a TI calculator, though, that'd be ideal. You're going to hit the stat button on your calculator. Then you're going to go over to tests. So stat and then tests. So stat button, over to tests. And what we're going to look for is a one proportion interval. So let's go down till we find, there it is. One proportion Z interval. Z just stands for normal, but we're doing a one proportion confidence interval. That's what this is. When you choose that, you have some very simple inputs here. It's like kind of on rails. The calculator will help you do all of the math. So in this case, we had 38 people out of 80, so 38 is our x, 80 is our n, and the confidence level we want to do is 95%, so 0.95, because it says what's a 95% confidence interval. So x, n, c level. You can do this by hand too. It's really not worth your time to do it by hand. Go ahead and go to calculate, and here is your interval. Very nice of them. They do it all the work for us. So the true proportion is probably between 36.5% or 36.6% and 58.4%. That's our interval. So again, I went to stat on your calculator. I went to stat, over to tests, and I scrolled all the way down until I found one prop Z int. We're doing a single sample, and we're doing a proportion confidence interval, one prop Z int. Again, if you don't have a TI calculator, I guarantee you that there are tons online that can do this for you. Oops. So that's how we get this confidence interval, 0.366 to 0.584. And then So step 3 is we go on to our conclusion, which is using that little sentence I had you memorize, hopefully you write down. We are 95% confident that the population proportion of health gym members that drive American-made cars is between 0.366 and 0.584. This is the interpretation of that interval. And those 3 steps are going to be repeated quite often. You want to check your conditions. You want to do your calculations. The calculator does that for us, which is kind of nice. And then you write your conclusion. And then, ooh, double trouble. That's exciting. So this is now going to be comparing populations. So we have 2 different things. So we took a random sample of 100 males and found that 27 were left-handed. And we took a second random sample of 100 females and found that 24 of them were left-handed. So now we have actually 2 point estimates. We have P at males, the proportion, our sample proportion for males, which is 27%, and P at females, which is the sample proportion for females. So we have our 2 proportions, and we want to compare these 2. For the conditions, you can check them. We want to make sure we have random samples. We do. You want to make sure that n times p and n times 1 minus p are both greater than or equal to 10. And you have to do it for both pairs. They're kind of skipping through that right now. And then they find this confidence interval. And I'll show you how to get this one in your calculator too. So just like before, you're going to hit the stat button on your calculator. But when you have double trouble, when you have 2 sample proportions, when you go to test, scroll down, we're no longer doing a 1 prop z int. We're doing a 2 prop z int because we have 2 sample proportions and we're doing a confidence interval based on those. We're finding the interval of the difference. So if you have 2 samples that you're working with, you're going to choose 2 prop z int. Again, it's kind of like on Rails. It's not going to be super difficult to input this information. It says you took a sample of 100 males and found out that 27, so 27 out of 100, just make sure you put it in the right order. The first population is 27 out of 100, or the first group, I should say. And the second group is going to be 24 out of 100 also, just from right here. And I forgot what level we were doing. Let me see if I can find it. It didn't specify, so we're probably going to do a 95% is my guess, since it didn't specify. Hopefully I'm correct in this guess. Let's check if I got the same answer they did. 95 is the most common, so that is what they got. Cool. So negative 0.091 to 0.15074. And if you're looking at this, you're thinking like, how do you get negative proportions? Well, what they're doing is they're subtracting the 2. So it is possible to get negatives when you subtract 2 numbers. So that's where this little negative part of the interval comes in. Most of the interval is positive because males do seem to be more likely to be left-handed, at least according to the sample. But there's a chance that the females have a higher proportion if you took another sample. When we get to the conclusion, we're going to write, we are 95% confident that the difference in population proportions, because we're finding the difference between the 2. Of males and females is between negative 0.091 and 0.151. And just in case, I can see how this might be a bit confusing. What they did, let me scoot this up. We just said we want to know the difference in proportion. So difference, which means subtraction, so males minus females in proportion of left-handed. I'll call them lefties. And so what we're doing here is we have this population of left-handed people that are male and a population of left-handed people that are female. This is male, female. And remember, this is the sampling distribution. There's a bunch of samples in here, and then there's a bunch of samples in here. And we're saying if we took a random sample from each of these, and we took the male proportion sample and subtracted the female proportion sample, we want to know what that difference would be. And according to our math, the difference would probably be somewhere between negative 0.091 and positive 0.151. So the proportion difference would be somewhere between here. And the most interesting thing to look for, and this is a habit you want to be whenever you're doing these two proportion ones, is the fact that 0 is in the interval. In the interval. And the reason why 0 is so important to look for is if the difference is 0, so if you do the proportion of males minus the proportion of females and you get 0, that's telling you that there's no difference between the two. Remember, this is an interval of plausible values. Plausible values. And what we're saying is, oh, apparently 0 is a plausible value for the difference, which means there might not be a difference between male and females when it comes to being left-handed. The fact that 0 is in that interval is telling us that there might not be a difference. That's a pretty important understanding. Confidence interval are the plausible values for the true proportions, in this case, true proportion difference. If 0 is in that interval, then it's plausible that the difference between the two is 0. This is plausible. So there might not be a difference between men and women just because 0 is in the interval. Most of the interval is positive. I recognize that. So it seems like maybe males are going to have higher proportion. But the fact that 0 is in there means that we don't have evidence one way or the other. Okay, let's see. So this is what I was saying. This is like an interpretation of the fact that 0 is in there. So since 0 is included in the confidence interval, there's not enough evidence that the proportion of males that are left-handed is significantly different than the proportion of females that are left-handed. This is entirely based on the fact that 0 is a plausible difference because it's in our interval. So 0 should always be mentioned when you're doing a double trouble problem. Whenever you have two proportions, 0 is what you should always look for in your interval. If 0 is in the interval, then there's not evidence of a difference. If 0 is not in the interval, though, then we do have evidence of a difference in one direction or the other. And I think that will do it. There's two homework for today. I think it's 65 and 66. And so you should maybe consider working on that. Let me see. How do I stop this video? It's always the end of, that's like my way of ending videos, is trying to figure out how to stop them and rambling. There we go.